is light. Light is a dance of electric field and magnetic field in the vacuum. So you have a electric field, which is of course up and down, and you have a magnetic field, which is in and out. And the dance between light is a dance between electric field and magnetic field in the vacuum, right? All right. When electric field and magnetic field dance in the vacuum, we humans perceive that as light, and we have a name for that. And dance with velocity v, of course. And what is the velocity v? Velocity v is, of course, you have 1 square root of epsilon and mu, and that is 3 times 10 raised to 8 meter per second. And if it does move in the medium, then it does with different velocity. For example, if it moves through the water, then a velocity of light is, of course, c over n. C is 3 times 10 raised to 8, and n is the index of refraction for the water, which is 1.33, which is 2.25 times 10 raised to 8. So what do you see over here? You see over here that light can move in the vacuum and in the water. Doesn't really matter, right? Light is a dance between electric field and magnetic field in the vacuum. When it moves in the vacuum, it dances with velocity c, 3 times 10 raised to 8. When it moves in the medium like water, it dances with velocity v, like 2.25 times 10 raised to 8. But the maximum light can get is 3 times 10 raised to 8. Today, we're going to be talking about like the understanding. Okay, so light is a transversal wave. In this transversal wave, so light is a transversal wave, right? Let's only focus on electric field, right? To simplify things, let's first understand the electric field only, up and down, right? So now, what is going on? It's moving with velocity v. So the particles, little particles, move up and down perpendicular with respect to the velocity v, right? The understanding of light is started with Sir Isaac Newton. Let's write the name, all the name that help us give us understanding of light. So Sir Isaac Newton. All right. Isaac Newton hypothesized that. What did he hypothesize? He hypothesized the light made of particles. Okay, light made of particles. All right. Now that understanding really did not last long, because Christian Huygens proposed that light is made of wave. Now Thomas Young, so this was 1666, this one 1678, this one 1801. Thomas Young did double slit experiment and show us that light actually show wave-like behavior. So 1801, everybody knows that light is no longer particle, it is wave, because that really helps us understand, explain, describe a light, right? So now, years later, you have the other people, such as Maxwell, who help us understand the light a little bit more. So Maxwell uses the Maxwell equation and calculate the speed of light. Of course, he used the ether, something called ether. All right. So Maxwell gave us the idea of light, and he used the ether to calculate the speed of light, and that takes us to Michelson, who gave us the idea that light doesn't need ether, right? Light doesn't need medium to move. That was done 1987. All right, he was the first American winning the Nobel Prize for his ideas, right? After Michelson, that take us to of course Planck. So Planck actually gave us this idea before Michelson. So Planck gave us the idea that the light, he didn't know what the hell he was talking about, but he gave us a math that he thought works, but he did not really understand. So he gave us something called E is equal to HF. Did not fully understand. He said the light, when in the hydrogen atom, for example, electron move down and it emits, photon, and then that human perceive as light, that comes as a packet which is discrete. If it's not discrete, then it doesn't work. So that's what he thought. So he just used a mathematical trick that works, but he had no understanding what actually E is equal to HF was. And that take us to genius Einstein, who really helped us understand E equal to HF, and he helped us understand E equal to HF by his photoelectric effect. For which he won the Nobel Prize in 1921. Okay, that take us to another genius. And now Einstein, by photoelectric effect, Einstein proved that, show that light is actually not wave, is actually particle. Now the problem again, the problem is getting bigger and bigger. It started with Newton, who thought light is a particle, and then Huygens, who thought light is a wave. Young proved that by double slit experiment that light is, of course, a wave, and then take us to Einstein, and who proved that light is not a wave, is particle, because his photoelectric effect, and of course the Planck also kind of E equal to HF, saying that light is discrete. Light is discrete. Now that takes us to de Broglie. De Broglie thought that if the particle can sometimes behave like wave, then wave can also sometimes behave like particle. So now de Broglie said that light is a wave and particle at the same time. So de Broglie. All right, so de Broglie said that light can be wave and particle, at the life has a wave particle duality. That takes us to the Bohr. Bohr realized that, okay, when you watch the electrons, then it behaves like particle. When you don't watch electron, it behaves like wave. So light really is tricky, because light involves with photon, that involves with electron, and behavioral electron, who knows what motivates the behavioral action. Nobody seems to understand the behavioral action. So that's what we're going to do in this video. We're going to try to understand the behavior of light, and there are 6 of them. Let me write them down. So all 6 of them. So we're going to start with reflection, and then refract. Okay, so let's write them down. Reflection, number 1, reflection. Number 2, refraction. Number 3, diffraction. Number 4, interference or superposition. Number 5, a Doppler effect. Number 6, let me see, you have polarization. All right, dispersion is a really special case with refraction, and critical angle is a special case of refraction, and also total internal reflection is a special case of refraction. So there are 3 special cases of refraction. Refraction is famous. So dispersion, we're going to say first a critical angle, critical angle, and then number 2, you're going to say total internal reflection, and then of course dispersion. All right, so let's start with a very simple question. Okay, let's start our conversation with a very, very simple question. What question I want to ask you is this one, right? Okay, I want to ask you the simple question. Okay, if I have a wall, right? This is called wall. This is me, right? And this is you. All right, you, and this is me. Why don't you see me? and I say, hello, you. Okay, there's a wall between you. Okay, and I ask you, do you? All right, let's do that. Hey, let's give it a name. This is, I don't know, Jack. Hey, Jack, do you see me? Hey, Jack, do you hear me? Let's do it again. Hey, Jack, do you see me? No, I don't. Hey, Jack, do you hear me? Yes, I do. What's going on? Why did Jack did not see me, but he heard me? Is because light cannot bend the way sound does. Light can't bend the way sound does. Why Jack heard me is because sound can bend. Sound can bend. Sound can bend the way so we call diffraction sound diffraction. Okay, and if lambda is bigger than the whole, you have the maximum diffraction, so that if there is a wall, you'll be able to hear from inside and outside the wall because of the way sound works. Okay, so if light does not bend, what does light do? Let's find out. Okay, how are we gonna find this out? Okay, so let's find out. Okay, so first, here's what we're gonna do. We're gonna have two surface 1 and surface 2. Of course, we're gonna have the normal. We have the normal, so we're gonna call it normal, and of course we're gonna call normal. All right, so we have scenario 1, we have scenario 2. Of course, we're gonna have something called incident ray. All right, and then we're gonna have a reflected ray. We have an incident ray, and then we have something like this. So by looking at this one, what do you think this one is? This one is, of course, a mirror, and this one is water. How do you know that? Okay, it's because very simple. Because this one is opaque, and this one is transparent. This one is transparent. This one is opaque, and this one is transparent. Okay, so what do you mean when you say opaque? This is what you mean. Here you have so let's talk about light pass through. Light pass through. Light doesn't pass through a mirror. However, light passes through water. Yeah, absolutely. Yes. You're going to say yes. What about see-through? Do you see through mirror? No, you don't see through mirror. Do you see through water? Yes, you do. All right, what else? Transmit. This is absorb. All right, some of the energy absorbed, by mirror, okay? Not 100% energy transferred, okay? So 1%, 2% energy get lost on the mirror, okay? And transmit. Transmit. All right. Angle theta, what about the angle? Angle theta is equal to angle final. Angle theta, incident angle is equal to final angle if and only if light goes from big n to small n, and incident angle is greater than the critical angle. Otherwise, we use the Snell's law, which is n1 sine theta 1 is equal to n2 sine theta 2. These are the technical difference, and now we're going to move to see the light behavior. We're going to study reflection, right? We're going to study this one. This one we're going to call, of course, we're going to call this one reflection, and this one we're going to call refraction. All right, application of this one is in GPS, And application of this one is in fiber optic cable. All right. Okay, now let's start our conversation with reflection. Okay, so to start our conversation with reflection, what are you going to do? We're going to draw, all right, so reflection. So you have a surface. So problem number one, right? You have a normal. Normal is 90 degrees with respect to the surface. Good. You have a light. We're going to call it incident ray. All right, incident. All right, we're going to mark it like this. And this is reflected ray. And we're going to call it like this. Incident is equal to reflected. Although some energy get lost, that doesn't affect the angle. What does it affect? It affects something else. It affects the energy. So this reflected ray does not have as much energy as this one. So energy before, energy after, not the same. However, the energy lost is very small. It doesn't affect the angle. Okay, so if this one is 30 degree, this one is also 30 degree. So if I give you a problem like this, if this is 50, I don't know, let's say 50. So what is the incident angle? Incident angle is 40. What is the reflected angle? Is also 40. How is that? This is 40 and this is 40. This is not how you measure the angle. This is just an information that allow you to find the incident angle. Don't forget that. Good. So now let me give you a second example. These are the easy example. Then we're gonna move on to something a little interesting. So I'm gonna have a meter one. I'm gonna have a meter two. Okay. So I have a light ray striking the meter one, and then striking the meter two. All right, with I don't know 30 degree. Okay, and then it reflects. Okay, it reflects. Okay, and then it reflects again. All right, it reflects again. Okay, so I want you to find this angle. What is this angle? Pretty easy. First thing you do is you draw the normal line. And you draw the normal line. You draw the normal line. You draw two normal lines. So you're gonna draw. If this is 30, this must be 60. So this must be 60 as well. Oh, I forgot to give you this one. Let's say this one was 130. Then this must be how much? This must be 30, 30, 60, 90. All right, so 130 plus 30 is 160. So this must be 20. Then this must be 70. This must be 70. So this must be 20. So you see how you can get this done, right? The reflection, the law of reflection allows you to find the missing angles. Good. Of course, you have to draw the normal line. Now, let's make things a little bit interesting. And that is, let's start with an analogy. So I often use this analogy because this is an interesting analogy. I have, let's say, my home to work. This is my home. This is my work. All right. So my home is my home. My work is Columbia University. All right. So what happened? I have path one. From home to Columbia University is D is equal to D1 is equal to, I don't know, it is 20 miles actually. Option 2, D2 is 40 miles. D3 is 50 miles. All right. All three options are gonna start from the home and end me up at my work, which is Columbia University. Now, which one should I take? Should I take the first one, second one, or third one? The most of the people, should I take the first one? Should I take the second one? Should I take the third one? And most of the people are gonna say D1. Of course, D1 doesn't have to be the best option. Why is that? Because D1 is for sure the shortest distance, but shortest distance between 2 points doesn't necessarily take least amount of time. Sometimes it does, but most of the time it doesn't. That's why we rely on GPS, because we don't see the future. GPS does. GPS use the refraction to see the future, to guide us to work, so that we don't have to blindly take the path that we think will take least amount of time. Usually doesn't, which is the shortest distance between 2 points. Good. All right, so now let's see how that GPS works. Let's start with something very simple. What is very simple? A problem. Okay. All right. So a problem is GPS works. Okay. So I have 1, I have 2, I have 3. I have three surfaces. They all are mirrored. This is mirrored. Mirror 1, mirror 2, mirror 3. Mirror 3. Okay, so what are you going to do with mirror 1? We're going to put a normal. We're going to put a normal. You're going to put a normal. After normal, we're going to put the, of course, the incident. 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 After incident, what are you going to do? We're going to put the reflected. 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 After reflected, what are you going to do? You're going to put some values. Put some values. You're going to finish this triangle. All right, let's finish this triangle. All right, I have few triangles. Okay, I have 6 triangles. Let's put some values. Okay, not blindly, so be careful. So let's put 4 meter, 4 meter, 4 meter. Then if this one 4, this must be 4 also. This must be 4 also. This must be 4 also. All right, now what are you going to do? We're going to put some value over here. So let's put 3 meter, 5 meter, 7 meter. All right. Now let's give you more values. So this one is, let's say, 7 meter. This one, let's say, 5 meter. This one, let's say, 3 meter. All right, now you're gonna see which one light gonna take. Which path light gonna take? Light has 3 paths now. Option 1, option 1, option 2, option 3. Which option light gonna take? Light not gonna take all 3. Light gonna take the one that shortest distance? No, of course not. Light gonna take the one that takes least amount of time. Which one is the least amount of time? Let's find out. So if you use Pythagorean theorem, which is c squared is equal to a squared plus b squared, you're gonna get this one is, of course, 3, 4, 5, and this one is 4, 7 is square root of 65, square root of 41, square root of 41, this is 5, square root of 65. All right, now you're going to start with the equation that you know, you love from your book. V is equal to VAT plus half AT squared. Of course, the acceleration of light is 0. Why is that? Light made of photon. Photon doesn't have mass. End of the story. Good. Now, D is equal to VAT. So what is time? Because we don't want to find the shortest distance. We want to find the the shortest time. Okay, so the time 1 is, of course, D over V. So D is, of course, 5 and square root of 65. 5 plus square root of 65 divided by 3 times 10 raised to 8. And that gives us T1 is equal to 4.35 times 10 raised to negative 8 second. All right, this one going to give us T2 is going to give you what? All right, so the square root of 41 plus square root of 41 divided by 3 times 10 raised to 8. So who is going to give you 4.327 times 10 raised to negative 8 second. And this one exactly give you the fast one. T3 going to give you 4.35 times 10 raised to negative 8. So of course now you see that why light going to take this one. Why? Because this one going to take the least amount of time. Now you probably think that light has three choices, but light doesn't have 3 choices. It has only 1 choice. Why? It knows what is the least, which path going to take the least amount of time all along, because it has a brain. Okay, what do I mean? You have path and you have time. You have path 1, path 2, path 3. 1, 2, 3. You have time 1, 4.3. You have time 2, 4.4 times 10 raised to 8 times 10 raised to negative 8. Of course. Now, path 1 takes how long? 4.4. 4.4. Path 2 takes 4.3. Path 3 takes 4.4. So now the least action, so this is called least action principle. Or of course you can also call it, I don't know, you can also call it Fermat principle, to show that the light takes the least, the path that takes the least amount of time. We're going to do one more problem and then we're going to move away from reflection. So these are the application of reflection. So what else also can do? Reflection, one of the phenomena of reflection is echo, right? So you can use, like sound echo, you can use light echo to find the distance between what? Galaxies, right? And when supernovas happen, right? When supernovas happen, that really help us. Supernova happen, that creates the cloud around the supernova, right? And then the sound that comes from the cloud is called the light echo, and we use the light echo to find the distance between two galaxies. Now, something like that we're gonna do. We have a moon on the moon. We have Earth. On the moon, Neil Armstrong, 1669, July 20, placed a meter. All right, now, okay, so you're going to send a signal from Earth, right, at t is equal to 0 second. We send the signal. T is equal to, so it hit the meter and it come back at t is equal to 2.56 second, it returns, okay? So light echo we're going to use to find the distance from Earth to the moon. And what is it? We're going to do two way. One way is, of course, the distance is VAT plus half AT squared, VAT. Okay, so the time is, or velocity is, let's use the time. Time is distance over velocity. Now, time is 2d over v. All right, and now we're going to do time is d over v. So we can do both. Time is 2d over v. We are finding the distance. So 2d is equal to what? Vt. So d is equal to Vt over 2. All right, so then d is equal to Vt. Okay, now then we have to use half, v half t. Why is that? Because it goes and come back. So we have to just use the, if you want to use this equation, traditional equation, we have to use half. So d is equal to v is 3 times 10 raised to 8, of course, and t is 2.56. And that divide by what? 2. And that is going to give you d is equal to 3.84 times 10 raised to 8 meters. And this one, of course, you're going to get the same thing. D is equal to v is 3 times 10 raised to 8 times 1 half t is 2.56. All right, so then give you 3.84 times 10 raised to 8 meter. Okay, so that's the, we finish with the reflection. Now we're going to do refraction. So let's do refraction. So what is refraction and why you like it? Okay, so refraction. All right, so refraction is very important, especially very important for us, refraction. Refraction, because it has 3 features. Number one, dispersion. Number 2, critical angle. Number 3, total internal reflection. Okay, all right, so what is refraction? Refraction is the bending of light. So refraction is bending of light when it changes the medium. Okay, so for example, when it moves from small n to big N, right? it bends. It bends to the normal. When it moves from, this is scenario 1. When it moves from, I don't know, big n to small n, it bends away from the normal. It bends away from the normal. Okay, now that's what we're going to learn right now. So let's say a light moves from air to water. Okay, so this is air, this is water. All right, this is, let's say, diamond, and let's say this is glass, and back to air. All right, so the light gonna move from all right, coming from the air and going to the water. So it's gonna bend. It's gonna bend exactly this way, because air and index of refraction is 1. Water index of refraction is 1.33. Diamond index of refraction is 2.42, and glass n is 1.53. Crown glass, and air n is 1. Okay, now let's see. I got, all right, so this is the calculator. I'm going to place it over here. If I need it, I'm going to use it. Okay, so now we're going to first find this angle. How are we going to find this angle? Is bandwidth. So this is coming. Incident angle is 30 degrees. All right, so now we're going to use Snell's law. What is Snell's law? Tells us n1 sine theta 1 is equal to n2 sine theta 2. So what is n1? N1 is 1. Why? N1 is 1. Sine theta 30 is equal to n2. Of course, n2 is 1.33. Sine refracted angle. This is what we are trying to find. So sine theta refracted is equal to sine 30, which is 0.5 divided by 1.33, right? So theta r is equal to, all right, sine inverse 0.5 divided by 1.33. So 0.5 divided by 1.33 must be 20 or something. Let me see. Sine 0.5 divided by 1.33, and that is 22. All right, so this one is 22. Angle is 22 degrees. As you see that it already bent toward the normal. Good. Now this one is now entering to diamond, right? This is entering to diamond, so we need another normal. Now this one is 1.33. This one is 2.42. Now it's going to even more bend to the normal. So now it's going to be more bending to the normal, right? So we're going to find it out how much, again using Snell's law. This time angle is this one is 1.33, right? And this one is of course 22. Okay, this one is entering to diamond, so 2.42. Everything else is same. So angle refraction is sine inverse of course 2.42. On the top you have 1.33 sine 22. So you have second sine, you have 1.33 sine 22. All right, all divided by 2.42, and that's supposed to be 11.88. So as you see, this is 11.88. So now we're gonna write 11 degree, just 12 degree. Nobody likes the angle in fraction, so we're gonna write 12 degree. Okay, now that enters to the glass. Okay, so it's entered to the glass, so you need another normal line. Now the good thing is the glass is 1.53, so this end is bigger than this end. So what is going to happen is going to move away from the normal. All right, so how much it moves away from the normal, that's what we're going to find. Okay, so n1 is 2.42 sine theta 12 degree is equal to n2, which is 1.53 count glass sine angle 2. So sine so just we're going to find angle 2 is equal to sine inverse. Of course, you have 1.53 on the top, on the down, 2.42 sine 12, so 19 degree. Now finally is entering the air, and we're going to find out what would that be. So this one is smaller than this one, so it's going to be um, moving away, moving even more away from the normal. All right, so how much away is moving from the normal? Let's find it out. So you have n1, which is 1.53, sine theta is 19 degree, is equal to n2, which is 1, sine theta 2. So theta 2 is now sine inverse, of course. You have 1.53 sine 19 degree. All right, so 30. You started with 30, you end up with 30. Okay, very nice. Okay, that's what happened because you back to air. So what do you expect other than 30-degree angle? That's pretty neat. Now, we're gonna now try to talk about dispersion. So refraction, just like reflection, discovered by Sir Isaac Newton. How did he discover it? By prism. What did he do? Before Sir Isaac Newton, the hypothesis was that the white light made of the sunlight made of white light, that's a reflection of God is pure, God is beautiful, just like the white light is made of one color, just white color. However, Sir Isaac Newton proved that wrong. So you have, what did he have? You have a prism. What did he do? He let the white color go through the prism. This is white color coming from the sun, and then it there is a dispersion. So there's a red, and then of course there is a orange. I don't have many colors, so I'm just going to do like this. Orange. Do I have orange? Yeah, I think so. I have orange. Okay, so that's red, that's orange. So it's like Roy-Z Beep. Roy-Z Beep. All right, red, orange, yellow. Do I have yellow? Okay, I think I have yellow. So that's yellow. And then I have green. Do I have green? I think so. Wow, I think I have a green. Unbelievable. So I have a green. I have a green. Okay. Does that look like green? I think so. Do I have blue? Yeah, I think I have a blue. Do I have indigo? No, I don't have indigo. I don't have violet. So that's as much as I can do. So I don't have indigo, I don't have violet. Okay, so this is what he did. So what does that mean? The light, when it goes through prism, it broke down to its smallest component, right? You cannot break down red light to a smaller component. Red is the fundamental as you can get. So the white light doesn't made of white light. White light makes of 7 components, and the 7 component would be 1, 2, 3, 4, 5, 6, 7: red, orange, yellow, green, blue, indigo, and violet. And then they have different wavelength, and they bend because the change of wavelength is responsible for different bending. Okay, so that is dispersion. Dispersion really give birth to the refraction. Now let's go to the critical angle. So what is critical angle? Critical angle only possible when light moves from big N to small n. So this is big N, this is a small n, this is normal. So critical angle possible when light moves from big N to small n. Okay, all right. And critical angle happens when incident angle, all right, go big, then at some point the refracted angle is exactly equal to 90 degree, and that's what we call critical angle. So what do we mean? All right, so this is incident angle, right? And if incident angle says this is 30 degree, it goes big, 40 degree, it goes big, 50 degree, it goes big, 60 degree. All right, at some point the incident angle is going to become critical angle if it goes big enough. When the reflected angle, if this one go this direction, this one gonna go this direction. As some when incident angle is critical angle, then this is exactly 90 degree. Okay, so then we're gonna call it, of course, what the name is, critical angle, because at critical angle the refraction is, there is no refraction, is only is lie on the x-axis. Okay, good, right. So let's find the equation using this understanding. So we're going to say that n1 sine theta 1 is equal to n2 sine theta 2. And of course, this is small n, this is big N. So we're going to say this is big N sine theta. We're going to say, of course, the critical angle is equal to small n. We're going to say sine 90 degree. Sine 90 degree is 1. So you're going to say big N sine critical is equal to n. So the critical angle is sine inverse small n over big N. Okay, so now let's use this formula to find the critical angle for the water to air. So what would be the critical angle from water to air? So that would be critical angle is equal to sine inverse. You have small n over 1.33. So the critical angle would be, I believe, 20. I'm not 100% sure. So inverse sine, you have 1 divided by 1.33, and that is 48. Oh, God, 49. Forget about 20, 49. All right. So when the angle become bigger than critical angle, then water started behave like the mirror, right? And application of critical angle, just like you saw, application of reflection in, I don't know, everything, like GPS made of, I don't know, reflection. This one, the application is everywhere. For example, the fiber optic cables. So let's take a look fiber optic cables. What about fiber optic cables? What do you know about fiber optic cables? If you consider fiber optic cables, then you'll see something good. What good are you going to see? Let's say fiber optic cable is an application of total internal reflection, and total internal reflection happens when the incident angle bigger than a critical angle, then total internal reflection happen. And then, for example, fiber optic cable. So fiber optic cable uses this physics in action. We call it fiber optic cable. So today's physics is tomorrow's technology. Fiber optic cables made the internet possible around the world, made us possible to create a global village grid. So this is a wire, okay? So we're gonna call it cladding. All right, inside the cladding, there is something called cable. Cable is made of glass. Cable has a big N, which is 1.49. The cladding has a small n, which is 1.47. All right, so what is the critical angle we're going to find? Because critical angle made it possible to go light, all right, and with total internal reflection from here to there, from North America to Europe to Africa to India to Australia, come back to America. Okay. So total critical angle is okay. Let's see, critical angle is equal to sine inverse small n over big N. So the critical angle should be what? Sine 1.47 divided by 1.49. So the critical angle is not sure, 80.6, I believe, 80.6 degree. All right, now anything bigger than incident angle is bigger than critical angle, then the light will behave like as if it is not in the glass or cable, it is in the mirror, right? So you have the cladding, small n, you have the cladding, small n, you have the big N, you have the cross section, all right? You have the normal line, you have the light coming with 81 degree, which is bigger than the critical angle. Then it hit the surface, but it never reflect. It's going to 100% reflect, and then 100% reflection, 100% reflection, 100%. We call it total internal reflection, and it lost zero energy. So it can pass the information without losing any information from one location to other location. Okay, so that is what you see it in action. Now that takes us to, I don't know, let's see, let's do Doppler effect. Okay. All right, so you're gonna do Doppler effect. After Doppler effect, we're going to do other two things quickly, and then the other three things quickly. We're going to finish it, try to finish it quickly, because this tutorial, I don't want it to be more than 1 hour long, but it is already more than 1 hour long. Hopefully not. Okay, so Doppler effect. So what is light Doppler effect? Light Doppler effect. Don't confuse it with sound Doppler effect. Sound Doppler effect, when the receiver doesn't receive the same information released by, when the observer doesn't receive the same information released by sources, right? That is sound Doppler effect. Now, deals with high pitch and low pitch, right? And what is then light Doppler effect? Light Doppler effect has to do with the stars, right? When the stars, you have Earth, and there is a star over here. All right, star emit lights all direction. All right, if a star move toward the Earth, then what we call it, blue shift. We're gonna try to understand why. If a star, this is Earth, this is scenario 2, this is Earth. If a star, for example, moving away from Earth, then we call redshift. All right, so let's see the star release the frequency 600, let's say 6 times 10 raised to 14 hertz. All right, and it's moving toward the Earth, right, with velocity 0.1 c. 0.1 c, what does that mean? It's fast, really fast. It's like c is the speed of light. Okay, so you are here on the Earth. You're gonna see the blue shift. What is that? Well, see. So the frequency perceived by you is equal to frequency released by the star is equal to square root of 1 plus minus v over c, 1 plus minus v over c. Okay, now what is this one? This one, the frequency perceived by you. This one, the frequency released by source. The velocity is relative velocity between Earth and the star, and c is the speed of light. Okay, now let's do the math over here. Let's see, the math does work out, and we're gonna move over there once we finish it over here. So you're gonna say 1. If it is moving toward, then this is gonna be big. Why is that? Because it's moving toward you. If the car moving toward you is high pitch, think about that. Okay, always think about something easy. Always think about sound diffraction. Sound, car moving to you, high pitch, moving away, low pitch. Okay, so then this is 1 plus v over c. Then this is 1 minus v over c. Now you can do one thing, and that's CC cancel. Why CC cancel? Because they do. C is the speed of light, 3 times 10 raised to 8. So you have 1 plus v, 1 minus v. Okay, so what is 1 plus v? 1 plus 0.1, 0.1 c, and 1 minus 0.1 c, CC cancel. So you have 1 plus 1 is 1.1, 1 minus 1 is 0.9. Excellent. So now we're going to plug that in. You're going to have 6 times 10 raised to 14, and we're going to have 1.1 divided by 0.9. So square root of 1.1 divided by 0.9. So 1.1 divided by 0.9. No. 1.1 divided by 0.9, and that would be 1.22. Square root of 1.22, that would be 1.10 times 6, and that would be 6.6. So that is frequency is 6.6 times 10 raised to 14 hertz. Of course, this is bigger than the frequency released by the star. So okay, what does that mean? The frequency perceived by the person on the Earth is bigger than frequency released by the source. That means you're going to see like compare the sound Doppler effect. We're not going to call high pitch, but we're going to call, in this case, blue shift. Blue shift and high pitch, you can say almost the same thing. They're not. Okay. All right. Very good. So this is done. Now, let's see the other one. Let's see the redshift. What causes the redshift? Similar idea. So you can finish it quickly. The idea is big, but math is very simple. Okay. Now, all right. So what is it? You have f frequency. This is perceived frequency, release frequency, 1 plus minus v over c, 1 plus minus v over c. Now, of course, you're going to write it down as f 1 minus. The top has to be small because it is moving away, like a car moving away from you, low pitch. So this is v over c, and this is 1. This is 1 plus v over c. C cancel. So then this is f 1 minus v, 1 plus v. All right, the frequency is really 6 times 10 raised to 14 hertz. And what else? You know something else. Velocity. Let's say it's moving away with velocity 0.1 c. Okay. Now what does that mean? F is equal to 6 times 10 raised to 14. All right. Don't forget the square root. All right. So now you have a square root. You have 1 minus 0.1 c, 1 plus 0.1 c. Okay, so on the top you have 6 times 14. On the top you have 0.9. On the bottom you have 1.1. All right, it's like scenario just like before, but opposite. So you have 0.9 divided by 1.1, which is 0.81, square root of 0.81, which is 0.9. 0.9 times 6, which is 5.4. So the frequency perceived by someone standing on Earth is 5.4 times 10 raised to 14 hertz. Of course, this one is smaller than the frequency released by the star. So this is, we're going to call redshift, which you can say is similar to something called the low pitch. All right, now this time we're going to go over double slit, and that is superposition, and then we're going to come back to diffraction. So let's do with the double slit experiment. Isaac, I want you to do me a favor. I want you to take a notebook and solve the problem. Okay, practice so that when you do 100%. Okay. All right. So 20 minutes and then you're going to go. Is that okay? All right. So all right, so what we're going to do is now we're going to do double slit. And double slit is the most famous experiment, one of the most famous experiment that gave the birth to, it actually gave the birth to quantum mechanics. So double slit experiment 1801. I'll take you to 1801. This is called Young double slit experiment, double slit. Why we are doing double slit? Because we are doing the superposition of light. We're going to call it, there is a reflection, there is an interference. Due to superposition, there is interference. There are two types of interference, destructive and constructive. Okay, good. Now, number one, what did he do? In 1801, he did a double slit. So we're going to do double slit, one slit, two slit. Great. All right, the distance between the two slit is, we're going to call it 0.0. Oh, no, let's help you understand what actually historically happened. So now let's make those small from there to here. Okay, scenario one, he had double slit, and this is the screen. The screen is d distance away from the slit. He threw marbles. All right, big object like marbles, because Newton hypothesized that, what was Newton hypothesis? The light is particle. Light made of light made of particle. Who said that? Newton. Light made of weight. Light made of wave. Who said that? Huygens. All right. So he is for finding out whether Newton is right or Huygens is right. Who is that? Young. Henry Young. What year he's testing it? 1801. What year Newton hypothesis? 1667. What year this guy hypothesis? 1678. Okay, very nice. So when he shoot what do you call it, small ball, and is gonna go in line with this slit, making two band, band 1 and band 2. All right, okay. So it made two fringes, right? Two bright fringes aligned with, in line with, you call it a slit. Nothing surprising, right? Nothing surprising. All right, good. Now, what he did, he used the double slit. Now, this time, instead of particles, these are particles, small balls are example of particles. Good. It behaves like a particle. It creates two bend, two fringes. Now he released water. So this is water. This is wave prompt of the water. Now water behave like water. So this water goes here and hit the screen, and this water gonna go like this. And you already see there is a problem. What problem you see? There is an interference from here. So this is, you have, this is 1, this is 2, this is 3, this is 4, this is 5, this is 6, something like that. And you have the bright fringes, right? You have the bright fringes. I'm gonna draw it nicely. Let's say bright fringes, and the dark fringes. Okay, so wave behave like wave. All right, the dark fringes, this is dark fringes, and this is bright fringes. Bright fringes. Bright fringes due to constructive interference. Constructive interference. The dark fringes due to destructive interference. All right, very nice, very cool, very easy, great. Now what he did, instead of this guy, he released light, because light is supposed to be like a particle. Newton said light is particle. So he got the slit 1, 2. It is a monochromatic light. What does that mean? One color light. So monochromatic light is a fancy way of saying one color light. Dispersion is one of the way you can separate the white color into is 7 smaller component. Okay, prism allow you to see the to broke the white light into red light, yellow light, orange light, and so on. Okay, so if you release the monochromatic light, which is, so this is light bulb, and this is light bulb. Okay, so it creates what? Like a ripple on the pond. Okay, all right. So this monochromatic light goes from fast lit, and there is a screen also reported. So what do you think? Is going to create two band? No, it did not create two band. In fact, it comes like this, and this one comes like this. Voila! Light behaves like water. It's supposed to behave like particle, but it does behave like a water. So who is right, Newton or Huygens? Now there is a problem. So Isaac Newton said light made of particle, and Christian Huygens said light made of waves. Now this famous guy, Young, 1801, sees that light behaves like a wave. We rejected Newton's hypothesis. Light is now become wave. Very good, because light does behave like a wave. Okay, so very good. Light is a wave. All right, good. Until, okay, of course, Niels Bohr gave an idea how the light, which is supposed to be a photon, who is due to electron jumps. So you send one electron every 1 hour, and electron, when electron goes through, how the hell that create waves? Because electron has to, electron has to, if electron goes to double slit, electron has to what? Split into two. All right. And one electron, you release one electron, is split into two. It takes the both slit and it creates what? Interference pattern. Just like that. Just like what? Just like water. How did this do this? It's supposed to create two fringes, but instead it creates interference patterns. It creates the bright fringes and dark fringes. What's that? Okay, it's because when you release electron, it is split into two or three or four, who knows, five. It takes both slit or no slit. Okay, now Niels Bohr decided to put an observer. So he put an observer. When he put an observer, then the wave behavior of light collapses and it behaves like particle. What the heck? So, it collapses the wave behavior just by observing it. Observation means measuring. Don't ask me what measuring is, nobody understands it. Okay, by looking at it, you changes the behavior because probably electron is conscious. Okay, great. So light has wave particle duality. Okay, that's our current understanding, that light behaves like wave and it behaves like particle. Very nice. Okay, now we're going to solve some of the problem, some of the interference problem, or one or two, and then we're going to move on to diffraction. After diffraction, we're going to do polarization, and that's it. That would be the last thing we will do. Okay, so diffraction, we're going to do a very simple math problem. You have a slit, one slit, you have a double slit, okay, and you have a screen 2 meters away. Okay, so you release what? Light get released from the bulb. This is monochromatic light, and the distance between these two slits is 0.02 millimeters. Okay, what else you need to know? This light, it has wavelength 600 nanometer. Okay, now the light is this is central, is as you see that, as I told you, that these create fringes. So this is called bright fringe, and this is called dark fringe. Dark fringe is due to destructive interference. The bright fringe is due to constructive interference. Very good. What we try to find is, first we're going to find, this is called center. This is called center. This is the first one. This is the second one. This is the third one. All right, this is -1, this is -2, this is -3. Okay, all right, so there are one more dark fringes than the bright fringes. You're going to see that. Why? So 1 2 3, 1 2 3 4. Okay, all right, so there are always one more dark fringes and then the bright fringes. Okay, one is the center, which is right. Okay, great. So we're gonna find the angle first. All right, we're gonna find the angle of what? The first one. So you're going to use the equation that we have: d sine theta is equal to m lambda. So the d is the distance between the state. Okay, good. And theta is the theta with respect to the central, the first fringes. M is the first one. M could be second one, third one, but we're going to find the first one. And lambda is the wavelength. So what is the sine theta? Sine theta is equal to m lambda over d. M is 1, lambda is 600 times 10 raised to negative 9, and d is 2 times 10 raised to negative 5. Of course, this is sine theta. 2 goes to 600, 300 times, of course. So sine theta is equal to, you have 300 times 10 raised to negative 4. So sine theta is equal to 0.03. So theta is equal to sine inverse 0.3. So theta is equal to 1.72 degree. So this is 1.72 degree. Now you're going to find the y. All right, how many centimeters this one away from the center? Okay, so that would be easy. So you're going to say we have a right angle triangle. We're going to say this is theta, this is y, this is 2 meters. Okay, so TOA will do the job. So tangent 1.72 is equal to opposite. This is y, and Jason, this is 2. So y is equal to 2, tangent 1.72, and then y is equal to not top on the top of my head. 2 times tangent 1.72, and that is 0.86. Oh, 0.6, 0.06 meter. So y is 6 centimeters. All right, so now we're going to try to find the distance. So this is the distance for the so now we're going to try to find how many fringes, right? So let's find how many fringes. Number one, okay, so right. So how many fringes? Fringes is equal to, so you're gonna the relationship inverse d over lambda. This is dark fringes. Okay, so d is of course 2 times 10 raised to negative 5, and lambda is 6 times 10 raised to negative 7. So 1 over 3 times 10 raised to 2. So this is 33. So 33 on the top, 33 on the bottom, so 66. Okay, so this is the dark fringes. So what about the bright fringes? So the bright fringes, so dark fringes, 66. Bright fringes, 33 minus 1, so 32. So bright fringes is 32 times 2, which is 64, plus the central, 65. As I said, the bright one is 1 less than the dark one. Okay, now we finish the interference, which is superposition, right? Double slit experiment, really, this one gave birth to the quantum mechanics. If you understand like 10% of this, that's really good. It's probably gonna change your life. Now let's take us to the diffraction. Light diffraction is if you understood this one, you will understand diffraction pretty quickly. And then we're going to do the polarization, which is like 2-minute business. and then we are done. I'm trying to finish it as quickly as possible because I don't want this tutorial becoming more than 1 hour long. Diffraction, light diffraction was discovered by Francesco Grimaldi, Italian, right? He was Italian and he discovered it 1675, pretty early. All right, so now sound diffraction. What is sound diffraction? Bending up a sound, right? Why do you see me when I am outside the door? You don't see me, I'm outside the door, but you hear me when I'm outside the door is because the sound can diffract the way it uses the hole, but light cannot diffract the way sound does. Okay, so what is the light doing then? Light diffract this way. So you're going to use the single slit. This is called single. So you are having light, monochromatic light. All right, this is a light bulb. It's going all direction. Like is equal on the front. And you take the slit. This is a slit. This is a screen 2 meters away, which is reporting what's going on with this light wave. And it coming, so it's 600 nanometer. And the hole is alpha is 0.02 millimeters, right? Okay, very nice. Okay, now it creates again interference pattern. Central, smaller, smaller fringes, bright and dark fringes. I mean, how many bright fringes? 1, 2, 3, 4, 5, 6. It's not gonna be 6, but I'm not gonna draw 32. Or 32 to this direction, 32 to that direction. I'm gonna call it central. All right, so this one is bright. This one is bright. This one is dark. This one is max. This one is mean. Okay, now what are you gonna do? You're gonna find the information we found before. If you didn't pay attention before, you're gonna understand it right now. So okay, so what's going on? So you're gonna find this is the angle, right? This is the central. Okay. All right, so you're gonna find the angle of the first max, right? First angle, this angle. So the equation is same. Alpha sine theta is equal to m lambda. So sine theta is equal to m lambda over alpha. Sine theta is equal to m is 1. We are trying to find this one. So this is 1 from the central. All right, so this is mean. So we are trying to find the mean. This is max, so this is mean. All right, mean. The angle of the mean, and then we're gonna find the angle of the bright one. Okay, let's see how it goes. Okay, sine theta is equal to m, which is 1, lambda, which is 600 times 10 raised to negative 9, and this is 2 times 10 raised to negative 5. So theta is equal to 1.72 degree. So this is 1.72 degree. Now the second thing we're going to find is the distance, y. So TOA is give you tangent. 1.72 is opposite, which is y, and Jason, which is 2. So y is equal to I believe 6 centimeters. 2 tangent 1.72. 2 tangent 1.72 is 6. We just found out a few seconds ago. 2 tangent 1.72, and that's give you 0.06, so 6 centimeters. So y is 6 centimeters. All right, now we're gonna find the other one. So the equation is y bright. This is y dark, or y mean, y max. Y bright is equal to m plus 1/2. So this is you have lambda L over what? our mu, our alpha. So m is 0, right? This one is 0. So with respect to this one, we are trying to find the bright one. So the distance. Okay, the bright one with respect to this one is 0 plus half. Lambda is 600. No, we're going to say 6 times 10 raised to negative 7. This is 2. And this is 2 times 10 raised to negative 5. 2 cancel. All right, so this 2 goes to 6 3 times. So you have 3 times 10 raised to negative 2. So the bright one is 3 centimeter. 3 centimeter. 3 centimeter. Okay, so the dark one is, the first dark one is, so the bright one is, okay, so let's see how we can understand it. All right, so this is the screen. Make it smaller. This is our central. This is our central. Okay, so this is the first. All right, so this is the first dark. So the first bright one is how much? First bright one is 3 centimeters. First bright one is 3 centimeters. So this to this is 3 centimeters. And this to this is 6 centimeters. So this is dark and this is bright. Finally, we're going to do polarization. Okay, so what is polarization and why it is important? Polarization is when the sunlight comes, light is polychromatic. What is polychromatic? It does have the electric field, magnetic field. All right, it's polychromatic. Okay, so we're gonna, just for simplicity, we're just gonna talk about the electric field, forget about magnetic field. So transversal wave, only the electric field matters. Okay, so light coming from sun moves all direction, which is polychromatic. Okay, however, that's bad for our eyes, so sometimes we have to polarize it. How? By polarizer machine. So we're gonna put it in the filter. If we do put it in filter, it's gonna polarize the light. It's gonna make it only oscillate 2 direction, up and down. So you're gonna say that this is intensity 0. All right, this is intensity 0. All right, so you're gonna make it intensity 0, which is the half. So you're gonna call it intensity 1. This is called intensity 0. So intensity 1 is half intensity 0. All right, so this light moves all direction, this light moves only 2 direction. We're gonna put it in the second filter. Second filter is this is our normal, is let's say 30 degree with respect to the normal. So we're gonna use the polarization law. So it goes to the second filter. Then we're gonna say that this is half the first one times cosine squared theta. What is cosine squared theta? This is 30 degrees, so cosine squared theta is square root of 3 over 2 and 1 over 2. This is cosine. This is sine. This is 30 degrees. So square root of 3 over 2 squared. So I2 is half I1, I0, initial intensity is 3 over 4. So what is the intensity of the light? Is 1 over 8 3/8. Okay, so as you see, by filtering, all right, by polar, you can make the light polarized, so that good for eyes. In a sunny day like today, June 27th, when you go outside, you see the reflection, and you don't want to see that reflection with polychromatic light. You want to see the monochromatic light, all right? So polarization is one way of making monochromatic, but it's not necessarily, don't confuse it with monochromatic. Monochromatic is like dispersion, when light goes through the prism, all right? So white light is can be divided into 7 of its smallest component. The polarization not necessarily is. Polarization is forcing the light to oscillate only one direction or two direction, and forcing light to lose intensity. Just finish this homework. This probably gonna change your life. Hopefully you're gonna get excited when you finish this homework.